easily. Okay, so we're dealing with this angle here was 135. Now that angle there is going to be, it should be smaller to cover the same arc. And you can do this using a ratio. Some of you try to do a ratio. The ratio is a little weird the way you do it. You can do a ratio. Mathematically, what we would do is find the arc here. So we know that arc is equal to S over theta. Oh, excuse me, S over R. And we're told that the theta angle is 135. We don't know the arc, so let's solve this equation for S. Most of us remember the connection between theta, S, and R with this first formula. If you can remember that connection, that's fine also. Doesn't matter. This is how I usually remember it, and then I go to whatever letter I need. So I need the arc. So that's going to be 12 times theta, which is 135. But that formula only works if we're in radians, so we have to do our conversion. And that S ends up being what? Somebody have that from the answer key? That S ends up being 9 pi, if we multiply that out and leave it in exact form. 9 pi. Any questions on that? So it's telling us that this distance right here is 9 pi. That's how long that is. So then we go to the big one. And that distance has to be the same. So now let's look at the big one. And the thing we don't know here is the angle. So let's use it in this form, S over R. So here, the S is going to be 9 pi. The R is going to be 18. We get pi over 2. And it asked for it in degrees. So we do 90 degrees. Let's see. OK, so now if you wanted to get at it with the ratio thing, you could say this to yourself. The angle in the bigger one, you know, has to be smaller. So if you take the angle in the smaller one, you have to multiply it by a fraction that is less than 1 so that you can reduce the 135. And so when you look at the ratio here, you could put, there's two ways you could form a ratio. You could do 12 over 18 or 18 over 12. If you do 18 over 12, that number is bigger than 1, so that's not going to help us. But if you did 12 over 18, which reduces to 2 over 3, that would actually work, and that will give it to us. So the ratio is a little awkward, but it does work. Yeah?
I did the ratio like that, and I got the same answer, but I got 0 points on that.
Oh, yeah. If I mark something that you think I did incorrectly, I don't know why I didn't look at my head. Yeah, okay, yeah. If there's something that I didn't mark correctly, definitely let me know. If I gave you too many points, it's up to you whether you let me know or not. If I gave you too many, you'll probably remain silent. But yeah, if you think that I had to grade a lot of tests. So if you think I marked one wrong, just let me know and I'll look at it and I'll give you points you deserve. All right. So is there anything else I wanted to mention on here? Those were the only two I really wanted to say anything about. So look at the answer key, and if you have any questions, shoot me an email, stop me during break, after class, and we'll go over them. All right, so let's jump to questions that you may have from 7.1 or 7.2. I picked out a couple that I definitely want to just look at because there's some different ways to do them. I want to make sure that you know at least a couple ways that you can approach some of these. Does anyone have a specific one? One or two? Oh, the other thing I have to mention. So grading. The grading is different. I do grading more like a GPA type of grading. And if you look in the content tab on D2L, there's a document that's called Grading Guidelines. And you should read that because that explains how I do my grading. So I basically look at every problem out of 5, take off 1 point for any trivial error, 2 points for any conceptual error. And this time I was super generous with the 1 point errors. In the future, for the rest of the tests, I will definitely be taking off. Jump off. And I think I had somebody else to solve. Oh, I'm sorry, Christian. lecture, I will definitely be taking off for all of those trivial errors. This time I was a little lax. If you didn't put your degree symbol, maybe I took off 1 point for 2 problems combined if you did it twice. Things like that. If you didn't put units, if you didn't do it twice in a row, I only took it off once. So I was super lax. In the next test, every time you don't put the units, I will take off a point. Every time you don't put the degree symbol, I'll take off a point. Every time you don't put the angle within parentheses, so if you write something like this, I'll take off the point. There has to be an angle in there, whatever it might be. It's got to be in there. So this time I was really sort of trying to break you in and let you know, make sure every time you make a trivial error, I'll take off a point. Conceptual error, 2 points. And so then what I do is average it just like a GPA type of thing. Add up the number of points. We had 15 questions. So I added up your points, divided by 15 to get an average, just like a GPA thing. And then there is a little chart in the grading guidelines document that tells you how I convert it back over to percents. So A is going to correspond to 90%, or a 4.0. 100% is going to correspond to 5.0. And then 80% will be 3.0. 70% is 2.5. And then 60% is 2. And 50% is 1. So that's how I'll go back and forth between those two systems, the points and the percentage. And so take a read on that. If you have any questions, if you're not sure how I got your number, your percent, let me know. Make sure I divide it by 15 properly and make sure I convert it to percents properly. So the idea behind this system is that I feel like it's a better way of measuring where you are, in the sense that classes before pre-calc, a lot of times you'll have like the first page just be super easy questions, and it's just like true, false, or matching, or some sort of very easy questions. And once you hit pre-calc, the question there's not a lot of simple questions. Most of them are kind of take some sort of thought. And so my idea is that if there's two major concepts and you know one super well and you don't know the other very well, what does that average to in a traditional grading system? F. Right? If there's two questions and you get one totally right and the next one you get totally wrong, but in practice, as you're moving through higher and higher level math courses, that doesn't accurately reflect your ability to do math. And so with the system I use, it's more balanced. If you do bad on one problem and good on another, it's not going to average to F. Okay, it's going to average a little higher than that. So that's why I like this system better. And it also allows me to just take off. Anytime I see a trivial error, I can take it off, and it's not going to kill you. Okay? But that said, you want to make sure you're not making trivial errors all over the place. Put your angles, put your units, put your degrees, do all those little things just to make sure you're not losing points. Okay. So, again, take a look, make sure you understand your grade, and if you see any discrepancy, let me know, and we'll go over it. So let's start with this question. It said, find an equivalent expression for -8 secant of x minus pi over 2. And there's two kind of standard ways to approach this. One is to use the odd-even properties. A couple of you did not use your odd-even properties on the first graph on the test. And you lost a point for that. So what I want to do here is rewrite the inside to represent the complement of x. So we had a theorem that we used that said cofunctions of complements are equal. That was a big theorem that we had earlier. Cofunctions of complements are equal. So if I had cosine of 10 degrees, I knew that was the same as sine of 80 degrees. Those are cofunctions and those are complements. And we can use that here. The issue is that when we write complements, like if I wrote an angle of x, its complement, if I do it in radians, because this problem's in radians, it would be pi over 2 minus x. That would be the complement of x. Pi over 2 minus x. 90 degrees minus x. That would be the complement. Here it's written as x minus pi over 2. So what I want to do is just try a little rewrite. So I'm going to write this as 8 secant. I'm going to factor out a -1, and then I have it in that form of complement. Now the minus, here's what some of you didn't do on the exam. Really important. When you have a leading minus, we use our odd-even properties to either take that minus and jump it out to the front or just erase it, depending on whether the function is odd or even. Is secant odd or even? Even, because its reciprocal is cosine, and cosine comes right off the y-axis, like an even function. It's symmetric about the y-axis. Cosine is even, secant is even, all the rest are odd. So that's an even function. With an even function, what do we do with that minus? Just goes away. We just erase it. Right? For an odd function, it jumps out to the front. If it's odd, it jumps. Okay, so now we have that. So now this question, yeah.
So if it was an odd function in that if the negative sign jumps out the front, what happens to the other negative sign?
What would happen? Positive.
Makes it positive.
Yep, makes it positive. Yep. So it acts like multiplication. So we'd have a minus times a minus. Very important. So now we're in this cofunction of complement stuff. What's the cofunction for secant? Cosecant, not the reciprocal. Right, the reciprocal is cosine, but the cofunction, secant and cosecant, those are the cofunctions, and the complement is just x. Right? X and pi over 2 minus x are complementary. And is that up there? Yeah, so there's A right there. So that's using odd-even properties, and cofunction of complements are equal. Cofunction of complements are equal. Okay, now another way to do this is using sum and difference identities. We dealt with sum and difference identities for sine and cosine, and I told you, those are the two that I expect you to know super well. This doesn't have a sine or a cosine in it, but we could rewrite this as minus 8 divided by cosine of x minus pi halves. Do that. And now we can use cosine of a difference. Now we can use cosine of a minus b. So let's do that. This will be negative 8 divided by. What's the first step if we're going to use cosine of a difference? What's our first step? Yep, cosine of alpha, cosine of the first angle. We can get that by erasing the second angle. And I'll just write it up here because we'll probably use it a few times today. So if we have cosine of alpha minus beta, this is going to be cosine of alpha and then cosine of beta, and then plus or minus. Plus, and we have cosine, cosine used up. Now we need sine, sine. So that's what we're going to use. So we erase the second angle, so we get cosine of x. And then the second factor of the first term is cosine of pi over 2. Now the minus is not part of that angle. Right, we separate that. We're thinking of the two angles as x is represented by alpha and pi over 2, not minus pi over 2 is beta. Cosine, cosine plus sine, sine. All right. Now we can do some evaluation here. What is cosine of pi over 2? 90 degrees, cosine's the x value, that is 0. So this is all going to go away because that factor has value 0. This factor, sine of pi over 2, 90 degrees, sine is the y value, up there is 1. So we get that. And now we can return to cosecant, and we would have that. So that's a way using the sum and difference identities that we learned on, wow, that was Thursday, last week. Thursday, last week. Yeah. Doesn't feel that long ago, but it was last week. Okay, just a multiplication problem to make sure you're sort of seeing how basic distribution laws apply. It's no harder than distributing numbers, but it looks harder because you have all these functions in there. But it's really not. So what we're going to think of here equals, we're going to take that cosine sine. That's one. That's it's two factors multiplied together, so we can think of it as one term. And it's going to be multiplied by secant, and then it has to be distributed over and multiplied by cosecant. And the piece I want to focus on here, I'm going to rewrite this with the commutative law of multiplication. Just for grins, I want to group the cosine next to the secant. This one I'm just going to leave the same. And I'm trying to sort of pair these off so that you can see the function cosine multiplied by its reciprocal. And what happens when you multiply a function by its reciprocal? What do you get? Yeah, 1, right. Think about it numerically. If you take the number 5, its reciprocal is 1/5. And if you multiply 5 by 1/5, you get 1. So a function multiplied by its reciprocal is 1. And so what we see is that we have two instances where we have a function multiplied by its reciprocal. So we get 1 in both those cases. So this is going to be sine x plus cosine of x. That will be the final simplified form. Right there. Does that make sense to everybody? So it's, if you're ever confused about some of the algebraic stuff, you can always go back and do it with numbers if you have to, just to make sure that you're understanding the sort of underlying properties. So here we're multiplying a function by its reciprocal, we get 1. Now, if jumping to that conclusion right away is, if it's not obvious, you can always do this. You can always say, hey, let's turn everything to sines and cosines. So we could turn secant into 1 over cosine x, and then you sort of see, oh yeah, that's cosine over cosine, which is in fact 1. Okay. Let's do one of these. It says here, rationalize the numerator. And this is different than what you did in college algebra. I don't know if you ever rationalized the numerator in college algebra. College algebra, 99, maybe 100% of the time, you rationalize the denominator. And once you get into calculus, most of us don't care whether you rationalize the numerator or the denominator. We generally just don't want square roots in both places. There's times, especially in calculus, where you're going to find out that rationalizing the numerator actually is more helpful in some cases. In college algebra, they just want you to get into that habit, get into the skill of being able to rationalize. And then later in calculus, there's going to be some analysis. Should I rationalize the top or the bottom? Doesn't matter. So let's take a look at this. First off, the square root of a fraction is a fraction of square roots. So we can do this. Okay. And just notice this note here. It says assume that all radicands are non-negative. That's a super important assumption. Hopefully you know why. I'll show you in a second here. If we wanted to rationalize the numerator, what do you think we're going to multiply top and bottom by? Square root sine x. Right, that's how you get rid of a square root. You multiply it by itself, and that will generate the following expression. So the square root of sine times the square root of sine is the square root of sine squared. And then downstairs we'll have the square root of cosine cubed times sine of x. All right, so what's the square root of sine squared? So, I hear this is the first and the most dominant thing I heard, sine x. Let me ask you another question for a second. Let's go over here. What is the square root of x squared? Okay, I hear x. So now let me, what's that? Let's see. So let's test. Let's suppose we let x equal -2. So if I plug -2 in there, -2 squared is 4, and the square root of 4 is 2. But is that equal to x? No. Square root of x squared, in general, is absolute value of x. So in general, you need to do that. Absolute value of x is the result of the square root of x squared. Unless you're told that you're only plugging in non-negative numbers. If you're plugging in non-negatives, then you know that your x value is 0 or positive. Then it's true that the square root of x squared is just x, if you know that x is not negative. So we have to be a little careful there. And it's not underscored enough in college algebra. In college algebra, there's always these little things. Oh, x is negative, never negative, never negative, never negative. So you just have to be careful. We're not always going to be dealing with that situation from here on out. So the square root of x squared is absolute x, not just x. So here, the square root of sine squared is just sine, but it's because we have that assumption up there that we're dealing with a non-negative radicand. All right, and then downtown, we can simplify this a little bit. That's cosine squared times cosine, so we could pull out one factor of cosine x. And then that would leave us with cosine x times sine x inside. And that gives us this one. Any questions on any of those steps or any of the concepts there? All right, let's go to our next task. Our next task, which is, it's not hard, but it's confusing. And what we want to do is verify identities. And it's not hard. We'll do some that take 3-4 steps, but there's no prescriptive process. So like graphing. A lot of you found the graphing pretty easy because I could say step 1, step 2, step 3, step 4, step 5. Do all those steps, you'll get it right. Cannot do that when we're verifying identities. When we're verifying identities, it's a process of trial and error. It's a process of, oh, this didn't work. I've got to try something else. And if you don't get in that mindset, which I know is hard for math students like to just follow the steps and get to the answer. You've got to get into the habit here of just trying stuff. Because if you don't try, you won't get to the result. It really is one of those things where you've got to just try different things. So first off, we talked about this last time. an identity is an equation that's true for all replacements of the variable for which the equation is defined. You know, so there's some of those oddball things like tangent. When we write tangent of x is equal to sine of x over cosine of x, that's an identity. It's true for all replacements of the variable. We're thinking of the variable here as an angle. The only issue is that we're not allowed to plug in pi over 2 plus pi k. Because if you plugged in pi over 2, cosine of pi over 2 is 0, you'd be dividing by 0. Tangent of pi over 2 is undefined. So we say this is true for all replacements of the variable x for which the equation is defined. You know, so if there's a bad x in there because it causes division by 0, we don't include that. Okay, so here's our process. This is, and one thing that these books do that kind of is misleading is that they just put an equal sign there. In math books these days, all equal signs they're not equal. So if you look at old math books, there was like 4 different symbols that meant something slightly different, kind of related to being equal, but maybe a little different. We had equivalent, we had equal, we had approximate. Nowadays, it just seems like they're using the same equal sign no matter what. And we don't know that this is true yet. We really should put an indicator here that tells us we don't know whether that equal is justified or not. We're trying to prove it. That's what this exercise is. We need to prove that the left side and the right side are the same. As soon as you write equals there, without the question mark, your instinct is, oh, let's multiply both sides by sine x. Let's multiply both sides by cosine x. Let's divide both sides by cosine x. And you cannot do that. When you're trying to prove that that equal sign is justified, you need to start with one side, manipulate it, and try to get to the other side. So you can't treat it like an equation. We're trying to prove that it is an equation. But it's not an equation until we prove it. And to prove it, you start from one side and try to get the other. Now, one thing you can do, which, like if you try to prove something, you can't prove it, and you're thinking, oh, is this really an identity? You can go to Desmos and graph. So what I did right there, I graphed y equals the left side of this equation. Y equals secant minus sine times tangent. And I got that graph. Does that graph resemble cosine x? Yeah, that's what cosine x looks like. So if you do that in Desmos, it doesn't prove that they're equal, because they could be off by the most minute amount, or they could be off in the tails somehow. So it doesn't prove it when you graph them that they look the same, but at least it gives you a darn good indication that you should be able to algebraically move through the process to prove it. Okay, so it sure looks like cosine x. Our hunch is that it is an identity. So here's how we do it. So we start with one side. I recommend starting with the harder, the more complicated side. It's easier to take a more complicated side and work it down into an easier looking side than it is to take an easier side and work it up into a more complicated looking side. Okay? So it's kind of like multiplication tends to be easier for most people than division. You know, multiplication is sort of working forward, division is sort of working backwards in some sense. So we're always going to choose the more complicated side. LHS, I use that to designate the left-hand side. So forget about the right-hand side. It's in our mind that we're trying to get to cosine, but we're not using that here. We're just going to manipulate this. So I do know that I want to end up with just cosine. I don't want secants and tangents. So the first thing that comes to my mind is let's turn everything into sines and cosines. That may help us. So we get that. Another general principle, our target has one term, has just cosine of x. Our starting side has two terms. So somehow those two terms need to be merged together. Well, right now, if we look at it, we see, oh, they're both fractions. So we can add those. And they actually are both fractions with the same denominator. This is multiplication, and you can think of that as over 1 if you need to. So this is sine squared over cosine. That's 1 over cosine. So they're already fractions with a common denominator. So we can make this 1 minus sine squared of x over cosine x. Any questions on that? And then, what is 1 minus sine squared? Cosine squared. All right, so remember, we have sine squared. I'll just write c's and s's here. Sine squared plus cosine squared equals 1. And I've mentioned this before, and I'll mention it again. You need to be able to get to the point where you kind of see the different permutations of this identity. Right? If you solve for sine squared, you see that sine squared is 1 minus cosine squared. If you solve for cosine squared, you see that cosine squared is 1 minus sine squared. So whenever you see a 1 minus cosine squared, it should be really close at hand that you could replace that with a sine squared. Anytime you see a 1 minus sine squared, it should be really, you should be able to see really quickly that you could replace that with cosine squared. Doesn't always work. That might not be the correct process for a particular identity. But you need to be able to see that you can always turn sine squared into 1 minus cosine squared and cosine squared into 1 minus sine squared. And so 1 minus sine squared is cosine squared. 1 cosine cancels. And that is the right-hand side of the equation, or the perspective equation. So we took the left-hand side, manipulated it with known facts, and got to the right-hand side. So now we've proved that the equal sign is justified. We've now proved that this is equal to that. Okay, so that's our process. Start with one side, known facts, get to the other side. And the only way to get decent at verifying identities is to do them, because there's no other way. All right, so here we have another one. And we want to start with one side and try to get to the other. This is one that the process, the technique I'm about to show you, it really is not going to matter if we pick the left or the right side. It's not going to matter. If you had to say one side more complicated than the other, anyone want to venture pick a side and say why you think it's more complicated? That's right. The right-hand side, I would agree, is more complicated than the left. The left side has a single term in the denominator. And you know that you could distribute that into the numerator if you had to break it apart really easily. So the left-hand side is easier because you could break it apart very easily. You could make it 1 over sine minus cosine over sine. So that's an obvious first step. The right-hand side, you've got 2 terms in the denominator. There's no way to parse that. You can't break that apart. So, and in this particular example, it's not going to really matter which side we pick. It's going to be just as hard, just as easy either way. But just so you know, I would consider that a more complicated expression. Okay. All right. Now here, this is a technique we are going to use, and it's going to come up again and again. And it's related to stuff you did in college algebra. It's just going to be a little different. In college algebra, if you had this expression, 1 plus the square root of 2, and you were asked to rationalize that denominator, what did you multiply top and bottom by? Yes. And what did you guys call that? Conjugate. And we're going to do something really similar here. The whole point of multiplying by that conjugate is that it caused some cancellation. It's caused some things to cancel. If you FOILed this out in the denominator, you had 1, and then you had plus root 2, minus root 2, and then minus 2. So those roots canceled out, and these turned into just a single number. So that's why it worked. You know, the middle term canceled out. And watch what will happen here when we multiply by the conjugate of the denominator. So we multiply top and bottom by 1 minus cos x. In the numerator, I'm not going to combine these yet. One thing you'll learn when you're working with identities is that this is a really good time not to skip steps, to go one step at a time, because there's all sorts of things that can happen with intermediate steps that you might not be aware of. So your instinct to distribute that across, pause. Just write it down as a pair of factors being multiplied together first. Now, in the denominator, do you see that we get 1? The outer is minus cosine x. The inner is plus cosine x. And the last will be minus cosine squared x. Everybody okay with that? Foiling. First, outer, inner, last. And just like over here, when you multiply conjugates, the inner and the outer go away. The inner and the outer go away. Let's just leave the numerator alone. Let's wait till we get the denominator caught up before we do anything else. So denominator, 1 minus cosine squared. Sine squared, right? And that is our goal. Our goal is to take these two terms and somehow manipulate them down into one term. That was our goal. Right? This denominator has one term. That denominator has two. So we're taking this denominator with two terms, and somehow we're trying to merge it into one term. So we multiply by the conjugate, and we're left with 1 minus cosine squared, and that is sine squared. Exactly. And now you can kind of see, oh, yeah, it made sense not to distribute this sign, because now what's going to happen? Cancel, right? We have multiplication up top, so this factor of sine is going to wipe out one of those factors of sine downtown. So we're going to be left with 1 minus cos in the numerator, 1 minus cosine x, and downstairs we're left with sine x. And that is the left-hand side. So we started with the right-hand side, manipulated, got the left-hand side. We never multiplied both sides by something. Start with one side, manipulate until you get the other side. Any step up there you want to talk about? Good? So no individual step is that hard. It's just that there's a bunch of little steps, and you're guessing. You're sort of saying, oh, what should I do? And I'm saying, do whatever you think you might be able to do. Just do something. You just got to do something. All right, so you guys try this one. I'll give you a hint. Pick the left side. Not much of a hint. Okay, so pick the left side. Use known facts to try to get the right-hand side. And I recommend stacking your work just the way I did. It helps you to just stay. You can sort of do a string across the board if you want. Just be really clear that you're going one step to the next. And don't all of a sudden treat it like an equation. Sure. So our main identity for Pythagorean is that. And if you subtract cosine squared to the right side, you get that. Or if you subtracted if you subtracted sine squared to the other side, you would get this. So these are two alternate ways to think about the Pythagorean identity. So anytime we see a 1 minus cosine squared, it can be rewritten as a sine squared. Or the other way. Yeah. fiddle around with it. Tempting. Very tempting. Okay. Let's go ahead and take a look at this. One thing, there's lots of ways you could go here. You could definitely try to multiply by a conjugate, just like we did in the other one, because we've seen that if you multiply by a conjugate, there's a good chance it will collapse to just one term. Right? Because we're in that same boat. We've got two terms here. We need to merge them into one term somehow. So we could multiply by a conjugate. That's a natural thing to try. Another thing that you could try is turn everything into sines and cosines and see if that works. Going to sines and cosines generally is a good thing to do most of the time. It generally is not going to hurt. Another thing we could do is try to clear out these functions. We could try to clear it out by, we know that the denominator here is cosine, the denominator here is sine. So we could multiply top and bottom by something to try to clear the little fractions. Lots of ways we could go. Let's go to sines and cosines, because that's a pretty natural choice. And it's not that complicated to do. So let's just see if that helps us. Okay, so we've got those two little fractions down there. And if we want to clear those little fractions out, what is the least common denominator in the denominator? So for those two little fractions down there, we've got that fraction and that fraction. What's the least common denominator? Sine x times cosine x, right? Because they're relatively prime. So what we can do is multiply top and bottom by that LCD. We multiply by the LCD of the denominator, we end up with the following. So again, in the numerator, let's not combine like what's it called? Let's not distribute yet. Let's just leave it as a string of multiplication for now. Let's just see how the denominator simplifies first. So in the denominator, we have to take this expression, sine times cosine. It needs to be multiplied by both terms down here. We need to share it with the denominator. So what is sine times cosine times 1 over cosine? Just sine. And what is sine times cosine times 1 over sine? Just cosine. Everybody see that? We distribute sine cosine to each little fraction. And so if that first one right there, well, I'm going to use s's and c's for a minute. So I have 1 over c, and I'm multiplying it by sine times cosine. That sine times cosine is in the numerator. So the cosines canceled, just giving sine. With that second fraction, we have 1 over sine, and we're multiplying by sine times cosine. The sines cancel. and we're left with just cosine. Just looks more complicated when you're dealing with trig functions, but the same properties that we used with fractions of numbers holds. If we did this off on the side with fractions of numbers, just as a quick example, if I had something like that, to clear the 3 and the 5, we would multiply top and bottom by 15. So in the top, we have 2 times 15, which we'll just leave it as 2 times 15. The 15 gets multiplied by the 1/3, giving us a 5. The 15 gets multiplied by the 1/5, giving us a 3. So that would end up being 30/8. Simplify that. That makes sense? So algebraic properties hold just like with numbers. Now we're golden. In the numerator, we have a sine plus cosine. In the denominator, we have a sine plus cosine. Those cancel. And those leave us, that leaves us with sine times cosine. And we think about our target. Our target was sine over secant. Well, cosine in the numerator is the same as secant in the denominator. And I think we started with the left-hand side and got the right-hand side. Cosine and secant are reciprocals of each other. So a cosine, you can replace cosine excuse me, with 1 over secant. Because they're reciprocals of each other. And that gives us the right-hand side. Any question on any of the steps up there? Let's go to another one. 10. So let's start with the left-hand side. That's got a cosine of a difference, so right away that's definitely looking more complicated on the left side. Got that. So we're going to try to get to the right-hand side. So first kind of obvious step is let's get rid of that cosine u minus v thing. Let's use our cosine of a difference. So we know that that's going to be cosine u cosine v, and then plus or minus. Plus, sine same, cosine opposite. That. It'll be very close. Very close. So we have 2 terms in the numerator, 1 term in the denominator. We can distribute that denominator into each term in the numerator. All right, we can share this denominator with, actually I want a different color, so we can divide it into that and divide it into that. Everyone okay with that? So if you have a plus b divided by c, the c divides into the a and the c divides into the b. So we're using this distribution property. So we're going to divide that denominator into each term in the numerator. Well, let's try it. And I won't cancel out right away. Let's do one step at a time. This is one type of math problem where it really can be a snake bite if you try to do 2 steps at once. It's always better to err on the side of 1 step at a time. And in this case, now we see, okay, factor of cosine u, vanish. Factor of sine v, vanish. We have multiplication in the numerator and denominator so we can cancel common factors. So over here, we're left with cosine over sine, which is cotangent. And then over here, we're left with sine over cosine, which is tangent of u. And I believe that they wrote, you don't really have to do this last step, but I believe they wrote it in that order, tangent plus cotangent. So that proves that the original was an equation. Any step up there you want to talk about? More explanation? Again, no single step is that complicated. It's just a matter of stringing them all together. Because at every step, there's a crossroads. It's like you could go this way, you could go that way. So it's a little bit tricky. All right, you guys try this one. This one's a little. This is a perfect one to do right before break. You feel nice and confident. You did it in 2 steps. Yeah, do it in 4 steps. A little bit during the break. Does everybody see the next step? Distribute that denominator. So cosine over cosine, and then sine over cosine. Cosine over cosine is 1, sine over cosine is tangent. And that is the right-hand side. Yeah. Well done. All right, let's take a 10-minute break. One more of these. Do one that has a few squares in it. Looks a little more complicated than the previous ones. And we'll start with the left side. And go from there. See what we get. We could, either one, the right side you could claim is more complicated because of the 4th power, but I would choose the left side. There's more stuff going on. And one tip when you're doing these, if you are dealing with just sines and cosines, there's a lot of writing sometimes. Totally fine to just use S for sine and C for cosine, if that helps you. Make it look a little bit more like algebra instead of trig. All right, so a couple of things happening here. We see that there is a common factor of cosine squared. Totally reasonable to try to factor that out. It's not an unreasonable thing. The 2 sine cosine, you might see that as a sine of 2 theta. You could use the double angle identity. I wouldn't recommend that because there's no double angles anywhere over here. So introducing a double angle is probably not the right way to go. Another thing you could say to yourself is that, hey, I know every trig function on the right is a sine. Right? The only trig functions over there are sine. So you could just say, hey, let's turn all the cosines into sines. And how do we turn cosines into sines? We would use this identity that cosine squared is 1 minus sine squared. So we could do that. That seems very plausible. That should work. It should all come out in the wash. So several ways you can go. Let's do it that way. Let's go ahead and say, hey, let's get rid of all the sines. All the cosines, sorry. Let's turn all the cosines into sines. So cosine squared is 1 minus sine squared. So that goes there. And then cosine to the fourth is cosine squared times cosine squared. So that's going to be 1 minus sine squared all squared. Let's distribute and see what happens. See if anything rolls out of here. Oh, there should be a theta right here. I always have to have an angle in the theta. Angle in the trig function right there. It should be a theta. So 2 sine squared theta times 1 is 2 sine squared theta. Minus 2 sine to the fourth of theta plus. Here we're going to FOIL. So we're going to have 1 minus 2 sine squared theta plus sine to the fourth of theta. So before we go on, let me know if there's any one of those steps that is not crystal clear. This first part we distributed, and then this down here we FOILed to get to that. Is that okay with everybody?
How did you get sine by the power of 4?
First one or second one?
The second one.
Second one, so we do first outer inner last. So we have 1 minus sine squared. Actually, I'll do it with just an S. That'll be a little bit easier. So 1 minus sine squared times 1 minus sine squared. So first is 1. Outer is minus sine squared. Inner is plus sine squared. And last is negative sine squared times negative sine squared, which is positive sine to the fourth.
Okay.
So it's negative sine squared times negative sine squared. Anything else up there? Okay, so we have a cancellation, right? Oh, I wrote one sign I wrote wrong here. Is this minus and plus? I treated it like a difference of squares instead of a perfect square trinomial. What should be there? Yeah, the inner is minus and the outer is minus. So that will end up being 1 minus 2 sine squared plus sine to the fourth. Yeah, sorry about that. Okay, so we have a term that wipes out here. This 2 sine squared and this negative 2 sine squared, they'll vanish. And we're left with exactly what we want to be left with. 1. And then minus 2 sine to the fourth plus 1 sine to the fourth is minus 1 sine to the fourth. That is the right-hand side. My guess is that's probably the fastest way. The chances of you always picking the fastest way is unlikely, so get in a habit. You might go 3-4 steps in and be like, oh gosh, I'm right back to where I started, essentially. So you just get in that habit of being persistent. All right. Now, this is what Jessica's really anxious to talk to you guys about, inverse trig functions. You dealt with you dealt with inverses in college algebra. And there was one really important property that a function had to satisfy in order to have an inverse that was a function. And what was that property? Right? Had to be 1-to-1. If you had a function like a parabola when you reflected it through the line y equals x, you ended up with a sideways parabola, which is not a function. It doesn't pass the vertical line test. So the condition that you had in college algebra was that the starting function had to be 1-to-1, which means it passes the horizontal line test, in order to have an inverse that was a function. So 1-to-1 means it passes the horizontal line test. To be a function, it passes the vertical line test. No vertical line meets it in more than one place. To be a 1-to-1 function, it has to pass the vertical to be a function, and then it has to pass the horizontal to be 1-to-1. Okay? So it's got to be 1-to-1 in order for the inverse to be a function. In its simplest context, inverses are found by interchanging all the x's and the y's. Right? So the x's become the y's become the x's. And so, thinking about trig functions, none of them are 1-to-1. Right? None of them pass the horizontal line test. Horizontal line meets any trig function. There is a horizontal line that meets every trig function in an infinite number of places. So they're definitely not 1-to-1. So what we do in order to get around this is restrict each of the 6 functions to an interval. And what we've done is created the largest possible interval on which the function is 1-to-1. And then we call that the restricted sine, or the restricted cosine, or the restricted tangent, or the restricted cosecant. So what we do with sine is go from right there, -pi/2 to right there, pi/2. Right? That piece of sine is 1-to-1. Not only is it 1-to-1, but it also gets at all of the y values for sine. The lowest y value for sine is -1. The highest y value is 1. So this captures all of the y values, and it is 1-to-1. So that is going to be the restricted sine. That will be what we base the inverse sine on. So this restricted sine, go from -pi/2 to pi/2, and the range is -1-to-1. So before we go down and look at this mumbo jumbo, x's become y's, y's become x's. When we're dealing with the regular graphing of a trig function, angles are on the x-axis, ratios are on the y-axis. When we do inverses, angles go on the y-axis, and ratios will go on the x-axis. So we're interchanging the roles that x and y play. So instead of x being an angle, y will be an angle. Instead of y being a ratio, x will be a ratio. So we're going to switch. So up here, when we think of a trig function, the first thing that pops into your mind should be ratio. If you hear sine of x, you should be thinking, oh, that's a ratio. That's some number between -1 and 1. It's some ratio. You're in a triangle. It's opposite over hypotenuse. You should be thinking sine of an angle is a ratio. Now, when we think about inverses, you should be thinking the opposite. You should be thinking the inverse of x is an angle. So now the x is going to be a ratio, and inverses will be angles. We're going to have angles as our outputs instead of ratios as our outputs. Is that clear? So for a trig function, you have a ratio as an output. For an inverse trig function, you have an angle for the output. Okay? So with a trig function, it's trig function of ratio is angle. For an inverse function, it's inverse of ratio is angle. All right, so here's what we do. The process you learned in college algebra, you interchange the x and the y, and then you solve for y. So to move the sine function to the other side, we have to use its inverse. And you first learned about that process when you tried to invert a famous function in college algebra called the exponential. Right? You had y equals e to the x. And the question was, well, let's find the inverse. So you interchange the x and the y. And then you had to solve for y. And what did you learn in college algebra to solve for the y? What function did you magically create that allowed you to solve for an exponent? Before college algebra, you couldn't solve for an exponent. So what did you do to both sides? Yep. So natural log of x. That is the same thing that we're doing now. Instead of coming up with a word that looks really different, this word is exponential, this word is logarithm, we're just going to put a little -1 up there. So instead of coming up with some other strange word for the inverse of sine, we'll just call it the inverse of sine. In college algebra, the inverse of the exponential is the log. Why they chose that terminology, I don't know. You almost think that they should just do e to the -1. Inverse exponential. But they called it the logarithm. For us, we'll just call the inverse of sine the inverse sine. So, the inverse sine is the blue function up here. The restricted sign is the black one. So all we did was turn the angles into ratios and the ratios into angles. We interchanged the coordinates. Let me highlight one ordered pair and show you. So this ordered pair is pi over 2 comma 1. So when we go to figure out the point on the inverse, we switch, we get 1 comma pi over 2. That's this point right here. So this point right here is 1 comma pi over 2. All right? And what you learn in college algebra, inverses and functions are just reflections about y equals x. That's the geometric relationship. They reflect through y equals x, through that line. All right. Let's relabel the axes because this looks really weird. For this blue function right there, the x interval, that's supposed to be a 1 down there. This is supposed to be pi over 2 up there. So let's just relabel the axes. And if we relabel the axes, this is what it looks like. So let's put, now the blue function looks a little bit easier to distinguish. We see that the domain for the blue function goes from -1 to 1. Blue, and the range goes from -pi over 2 to pi over 2. All right, so that, let's do an example. So inverse sine of 1/2. So what you're saying to yourself when you see this, you're saying, what angle between -pi over 2 and pi over 2 has a sine value of 1/2. So what is the angle that has a sine value of 1/2? And we're restricting ourselves. The angle is between -pi over 2 and pi over 2. If you think about the unit circle, that means it's on the right side of the unit circle, -pi over 2 to pi over 2. So we're saying, what is the angle on the right side of the unit circle that has a sine value of 1/2? There is only one angle on the right side of the unit circle that has a sine value of 1/2. And that's it, pi over 6. Every time you see an inverse trig function, angle. It's an angle. Inverse trig functions are angles. We did inverse sine of -√2 over 2. We'd be saying, what angle between -pi over 2 and pi over 2, so angle on the right side of the unit circle, has a sine value of -√2 over 2. So which quadrant are we in, 1 or 4? Bisecting quadrant 4. Now the one mistake that people tend to make, we have to stay on the right side of the circle. We're staying between -pi over 2 and pi over 2. We can't spin around and go 7 pi over 4. That's not between -pi over 2 and pi over 2. Even though in standard position, 7 pi over 4 brings you to the same place. It's coterminal. But if we're going to stay between -pi over 2 and pi over 2, to get down there, we would do -pi over 4. That is the angle that's restricted between -pi over 2 and pi over 2. It's restricted to the right side of the circle. Okay. We'll do lots more of those very shortly. Restricted cosine. Cosine, same thing. It's not 1 to 1, right? It's constantly repeating. So we restrict it. We say, hey, if we go 0 to pi, that piece of it is 1 to 1. That passes the horizontal line test. So that piece will have an inverse. And let's create the inverse graph here. So this point right here is 0, 1. This point right here is pi over 2, 0. And this point here is pi, -1. So to find the 3 corresponding points on the inverse, switch the x's and y's. So 1, 0, 0, 1 becomes 1, 0. So that's 1. That point, pi over 2, 0 becomes 0, pi over 2. And we're moving the angles to the y-axis now. Ratios on the x-axis. And then pi, -1. We're going to make that -1, pi. We'll put that right there. I guess I don't need to. I can just do that. Pi. Now let's draw the graph. So this one wraps around the x-axis. This one's going to wrap around the y-axis. So it's going to do that kind of thing. So that will be a picture of y equals inverse cosine of x. So notice that this is an angle on the right side of the unit circle. Let's just do a couple of quick examples. We'll do a lot more of these in a moment, but let's just throw one in here. Throw 2 in here. Where that thing came from. All right. Whoa! What the heck? Didn't I just erase? No idea. Oh, someone's hacked into our board. A little harder to hack into our system now. It was a long time ago. I was teaching in that classroom over there, and I was teaching like I think it was a Calc 3 class, and I was standing there, and all of a sudden, writing started coming across the smartboard. This big smiley face and a ha-ha. We're just sitting there looking at the board. Some student had hacked into the computer there from another classroom and was writing on my board. I don't think it's possible these days for that to happen, but it was pretty funny. So the way that I want you to think about this, I want you to say to yourself, this is the angle between 0 and pi. And if we think unit circle, we're thinking the top half of the unit circle. Angle between 0 and pi with a cosine value of √3/2. There's only one. Right? These are functions, so there's only one answer. So angle between 0 and pi, where a cosine value is √3/2, pi over 6. It's the only place. Pi over 6. It's the only place. Second one, inverse cosine of -√2/2, angle on the top half of the circle, with a cosine value of -√2/2. So 3 pi over 4. I'll try to erase you again. Ooh, okay. All right, good. Inverse tangent. So for tangent, we look at the largest piece that is 1 to 1. The largest piece that's 1 to 1 is from -pi/2 to pi/2. Here we don't include the endpoints because we have asymptotes there. But that restricted part of tangent is 1 to 1, that middle piece there. Domain, range. Now we interchange. So those two vertical lines, x equals pi/2, x equals -pi/2, if we switch all the x's and the y's, x equals pi/2 becomes y equals pi/2, which is right there. So this is the line, y equals pi/2. The line up here, x equals -pi/2, becomes the line, y equals -pi/2. this point is certainly on the graph, the origin, because this point is 0, 0, so if we interchange, we get that. Now, instead of picking points this time, let's just sort of think a little bit more generally. So as the ratio, up here, as the angle approaches pi over 2, the ratio is approaching infinity. As the angle approaches pi over 2, the ratio is approaching infinity. So we want to switch that now. We want to say, as the angle approaches pi over 2, the ratio is approaching infinity. So we're doing this kind of thing. So that will be our graph. It's a really interesting graph because it's one of the first, if not the first, that you've seen that has two horizontal asymptotes. Most of the graphs, if not all the ones you've seen, have only had one. This is a picture of inverse tangent. It has two horizontal asymptotes. This is the graph of an inverse function that you need to know the best. This inverse trig function is the one that will show up in calculus 1, 2, and 3 way more than any other inverse trig function. And it's because the graph is so interesting. It's got these asymptotes, so you can talk about the end behavior very easily. You can see as x goes to infinity, this gets close to pi over 2. As x goes to minus infinity, the angle gets close to minus pi over 2. There's a lot of things in calculus that this function is going to be analyzed for. So that one's the one you need to actually know the best. I won't ask you to graph any inverse trig function on the test, but that one is one that you want to be most familiar with. So let's do a couple of little examples. Let's do inverse tangent of, let's say, minus 1, and let's say, let's do a root 3 over 3. Okay, so inverse tangent is an angle between minus pi over 2 and pi over 2. So if we're thinking about the unit circle, back on the right-hand side, like inverse sine, right side of the unit circle. Inverse sine, inverse tangent, right side of the circle. Inverse cosine, top half of the circle. So inverse tangent's on the right. So that says what angle on the right has a tangent value of -1? On the right. Negative pi over 4. And again, we can't say 7 pi over 4. We have to stay on the right. Can't spin around and go to coterminal at 7 pi over 4. Inverse tangent of root 3 over 3. Angle on the right. Right away we know we're in quadrant 1. That's where the tangent values are 1. Excuse me, are positive. So we know we're in quadrant 1. So quadrant 1, tangent value root 3 over 3. On the 12-sector circle, we had two terminal rays. One had a slope of root 3, and the less steep one was root 3 over 3. So that's going to be pi over 6. So at pi over 3, it's root 3. Pi over 6, it's root 3 over 3. All right, good. So here's our little summary, a practical summary. I think it's easier to remember visually if you think about the unit circle. I think it's easier to visualize and say, oh yeah, the inverse cosine's an angle on top. Instead of keeping these endpoints in your mind all the time, it's a quick, easy summary. Inverse cosine's on top, inverse sine, inverse tangent on the right. The most important thing is that the word angle jumps into your mind every time you see an inverse. You think angle. That's the first thing. Always think angle. All right. So let's do a few of these. So I've indicated the part of the circle it's on. Let's just do a few. So inverse sine of -1/2. That's saying the angle on the right with a sine value of -1/2. So that makes me think of the 12-sector circle, because I know the coordinates are 1/2 and √3/2. So the angle with a sine value of -1/2 is right there. And how would we describe that angle? Yep, exactly. So this is equal to -π/6. So we cannot leave the right side of the circle. Really? Oh, okay. That's how it works. We cannot leave the right side of the circle. So the way we would draw that angle is it's right here. It's down like that. Got to stay on the right. All right, middle one. Inverse cosine of 0. So that tells us that we want the angle. It's only one. These are functions. The angle in the top half of the circle with a cosine value of 0, right there. So that angle is π/2. Let's see if it works this time. All right, last one. That's saying find the angle on the right with a tangent value of -1. So that's right down there. And that will be -π/4. It's so puzzling. So puzzling. I'm not using you anymore. Go back to using this pen. So that's -π/4. All right. Let's talk about the other three for a few minutes. And before we do the other three, let me give you, I want you to work on a couple. Let me put some up here for you guys to work on. All right, so some examples. So let's see you do these guys. Start with inverse sine of 0. Try those out. All right. Let's go through. First, let's just identify where the angle would live. So inverse sine, right or top? Right. Inverse cosine, right or top? Top. Inverse tangent, right. Inverse tangent, right. Inverse cosine, top. Inverse sine, right. So that's the first step. Angle on top or on right. First step. So that inverse sine of 0 problem, we're saying angle on the right with a sine value of 0. So we want where the y-coordinate is 0. Is that right there? And what angle is that? 0. Second one, angle on top with a cosine value of negative root 2 over 2. Right there. So how do we describe that angle? Yep, 3 pi over 4. Good. Next one, inverse tan of negative root 3, angle on the right. Quadrant 1 or 4? 4. Steep or less steep? Steep. Minus root 3 will be the steeper one. Minus root 3 over 3 would be the less steep one. And that angle is minus pi over 3. Inverse sine of 1. Angle on the right with a sine value of negative 1. Down there. Y-coordinates negative 1. How do you think we're going to describe that? Negative pi over 2. Not 3 pi over 2. Not 3 pi over 2. Negative pi over 2. There's only one answer for each of these. These are functions. Functions have one answer only. Inverse cosine, top half. Negative root 3 over 2. So we want the angle with the cosine value of negative root 3 over 2. 12-sector circle right there. And that is, what's that angle? 5 pi over 6. Last one, inverse tan of 0. Angle on the right with a tangent value of 0. Is that right there? The terminal ray has to have a slope of 0. And what's that angle in radians? 0. What's that angle in degrees? 0. Except we should say 0 degrees. We're in degrees. So if you look online or in old books, you're going to often see this expression. You're going to see, instead of them writing tan with a little minus 1, a lot of times you'll see arctan, especially in really old books, where it was a lot harder in printed books to make this exponent thing happen. A lot of books write that. Same meaning, arctan. Arctan just means inverse tangent. Same thing. So it means exactly the same thing if you see an arc. Or if you hear somebody say arc sine, it just means inverse sine. Sometimes you'll hear that. So just be aware of that. No big deal. And the reason that it works totally fine, your last exam we looked at this situation. Actually, let me grab a unit circle that's already made. That'll be a little easier. All right, so the relationship that we saw in the last test that connected angle, arc, and radius, if this was a unit circle, that's theta, that's s, we know that theta is equal to s divided by r. So in this case, we have s divided by 1. So theta and s have the same numerical value. Okay? Unit-wise, you may say, oh, well, s will have units of length because it's a distance. Theta would have units of radians if we're in radians. But they have the same numerical value. Right? So angle and arc are the same. So that's why they'll use the word arc. So this, another way to think of this is find the angle on the right that has an arc. I don't want to say that. So this, you could interpret it this way. Find the arc on the right that has a tangent value of negative root 3. Find the arc on the right instead of the angle on the right. So it works, but we don't use this very often anymore. But if you see it, it just means the same thing. All right, let's talk about the other three. So the other three, you can certainly, and I kind of recommend just doing them from scratch and not memorizing these formulas, but they're not that hard to memorize, especially the first two. We'll do a few examples. So inverse cosecant and inverse sine, they line up on the right-hand side. And the connection between the two is that we can find the inverse cosecant by finding the inverse sine of the reciprocal. So we take the t value, find the reciprocal, and then we can use the inverse sine function. Or you could just go from scratch and say what angle on the right has a cosecant value of whatever it is. You can do it directly the way we just did the other three. But some people like to use these little formulas. Totally up to you. Inverse secant, you can find inverse cosine of the reciprocal. Works totally fine. And that matches. Inverse cosine is on top, just like inverse secant is on top. Inverse cotangent. So this one's a little bit weirder. And actually, I have my arc drawn wrong there. I can't believe I have the arc drawn wrong there. That's not cool. This thing is supposed to be on the top half for inverse cotangent. Inverse cotangent is an angle between 0 and pi, not an angle between minus pi over 2 and pi over 2. So inverse tangent is between minus pi over pi over 2. And then when we do this subtraction thing, we're going to end up with an angle between 0 and pi, not negative pi. We're going to be on top instead of on the right. And that's very easy to think about in your head based on the last test where we were graphing tangent and cotangent. The first period of tangent goes from minus pi over 2 to pi over 2, but the first period of cotangent goes from 0 to pi. So for the cotangent function, it goes 0 to pi. So for inverse cotangent, we still want that angle to go from 0 to pi. Top half. Top half of the circle. All right, so let's do a few examples of these guys. So this first one, we could do it two ways. The way I would recommend is instead of memorizing a new formula, I would say to myself that we have an angle. I think we just need the 4-sector circle for this one. I would say to myself, the inverse cosecant is also on the right, like the inverse sine. So cosecant and sine are reciprocals. They're going to be on the same side. So inverse cosecant's over here. Bless you. And I would say this is the angle on the right that has a cosecant value of -1. A cosecant value of -1. We definitely know that we're going to be dealing with points that are probably the top and the bottom, because those are or the right maybe if you're a little bit unsure. This point is 1, 0. This point is 0, -1. This point 0, 1. So cosecant is the reciprocal of the y-coordinate. The y-coordinate is sine. cosecant's the reciprocal of the y coordinate. So if you do it directly, you would be saying what angle on the right has a cosecant of -1? In other words, what angle on the right has a y reciprocal that's equal to -1? And that's going to be right down there at -pi/2. So that would be the direct way to do it. The way using the formula, you would say inverse cosecant of -1 is equal to the inverse sine of the reciprocal of -1, which is the inverse sine of -1. And then you'd be saying the same thing in your head, angle on the right with a sine value of -1, which is right there at -pi/2. Second one, inverse secant, that's going to be on the top half of the circle, just like inverse cosine. So here, if we do it directly, we'd be saying what angle on the top half of the circle has a secant value of 2. If the secant value is 2, the cosine value is 1/2. So we're trying to figure out where the cosine value is 1/2. We're going to look right here. That's 1/2 comma √3/2. And that will match what we're looking for. So that will be pi/3 as our answer. If you were to write out the formula method, you would say inverse secant of 2 is the inverse cosine of 1/2. And that's pi/3. Now, inverse cotangent is definitely one I think using the formula is more complicated for. You got to do pi/2 minus inverse tangent of the same angle. I think it's a little more complicated. I would do it directly. I would just say, let's look at a unit circle, 12 sector, because that's where we see the √3/3 and the √3 for tangent values. Inverse cotangent is going to be an angle on the top half of the circle. So in the big picture, there's going to be 3 on top and 3 on the right. So inverse cosine and inverse secant and inverse cotangent are on top. Inverse sine, inverse cosecant, and inverse tangent are on the right. They'll be split evenly, 3 and 3. All right, so this tells us angle on top with a cotangent value of -√3/3. Now, if it was a tangent value, we would be looking at the less steep terminal ray if it was tangent. But it's inverse cotangent, so we're actually looking for the steeper one, and it will be there. To convince ourselves, let's look at the ordered pair, -1/2 √3/2. Cotangent is the x value divided by the y value. The 2's cancel, we get -1/√3. And if we rationalize the denominator, we get minus √3/3. So that would be the angle that has a cotangent value of minus √3/3. Yeah? And what's that angle? Try again. Unless I misheard. What's that angle? 2pi/3. Yeah. Maybe that's what you said. I only heard pi/3. That's why I was asking for a reclaim. All right, is that okay with everybody? All right, let's try a few of these ones. Let's put in a new page and give you some to try. try this. If you can scramble your mind to be thinking about angles as outputs instead of ratios as outputs. Inverse cosecant, top or right? It's going to be the right. It's the same as inverse sine. So inverse sine, inverse cosecant, those are both on the right. Inverse secant, top or right? Just like inverse cosine. Inverse cotangent, top or right? Top. So this one's just switched up from its companion. Inverse tan is on the right, inverse cotan is on the top. So this guy here says angle on the right with a cosecant of -2. If the cosecant is -2, the sine is -1/2. So we want to look over here for a sine value of -1/2, and that's right there. And how would we call that angle? -π/6. Next one says inverse secant of -2/√3. So that's an angle on top with a secant value equal to -2/√3. If secant is -2/√3, cosine is -√3/2. So -√3/2 for cosine is right there. And that angle is 5π/6. Next one, inverse cotan is on top with a cotangent value of -√3. Cotangent of -√3. So the tangent would be -1/√3. And -1/√3, if we rationalize, would be this. So top half of the circle with a tangent value of -√3/3, that's the less steep terminal ray, because we're dividing by 3. So it would be that one. So another way to think of it is that with inverse, or with tangent, the less steep one is √3/3. With cotangent, it's just reversed. So with cotangent, √3 is the less steep. And if it was inverse cotangent of √3/3, that would be the more steep. So it just has that reverse effect. And that angle, again, is 5π/6. Let's get those three over there. Inverse cosecant, angle on the right, where the cosecant is -√2. So that means the sine is -1/√2 or -√2/2. So over there, where the sine is -√2/2, that right there, where the sine value is -√2/2, And what's that angle? Yeah, negative pi over 4. Inverse secant, angle on top, where the secant value is negative 1, which means the reciprocal of secant, which is cosine, is also negative 1. So angle on top where the cosine is negative 1. Pi, exactly. There, pi. Inverse cotangents on top, where the cotangent value is negative 1, or the tangent value is negative 1. If you take the reciprocal of negative 1, you get negative 1. So we want to know where the tangent value is negative 1. And that would be right there. Tangent value of negative 1. And that is 3 pi over 4. All right, so those are the sort of basic facts with inverse trig functions. Really important to sort of be able to go through that process step by step, figure out which angle it is and how to find it. And then we make it look even nastier. And we compose our inverse trig functions with regular trig functions. So now we have compositions. Compositions of trig functions and inverse trig functions. All right. Let's do these two, and let's see what happens. All right. With that first one, and with any composition in general, usually you go to the inside, try to evaluate what's the innermost part of the composition, and then work your way out. That's usually what we do. And let's see if it works. So here, let's leave the inverse sign alone. But maybe in the back of our mind, we're thinking the very final output should be an angle on the right half of the unit circle, because inverse sign's on the outside. So at the very end, we should end up with an angle on the right. At the very end. All right. But before we get to that, let's just focus on the inside. That says tangent of negative pi over 4. We can evaluate that. Tangent of negative pi over 4. We go down to negative pi over 4, and that tangent value is negative 1. It's the slope of the terminal ray. And if we're going to go down pi over 4, we're in quadrant 4, bisecting it, slope's negative 1. So now we go to the outside function, and we're thinking an angle on the right side of the circle with a sine value of negative 1. Angle on the right, sine value of negative 1. What angle does that have to be? Negative pi over 2. They look way more complicated than they are. Just go all the way to the inside first and work your way out, step by step, and you'll be able to do it. Now, before we do this crazy looking one, that one's hard. I want to do another one. Let's suppose we compose the inverse cosine with cosine. So the inside is a cosine function, the outside's its inverse. What would you like to happen? Yeah, wouldn't you love to just say, hey, that's 7 pi over 6? And there are times where that will happen. But when we look at that outside function, inverse cosine, is that on the top or the right of the unit circle? It's on the top. Is 7 pi over 6 on the top half of the unit circle? No. So we know that that's not going to happen. We know that those can't just cancel. Because the outside function is inverse cosine. We know that lives on the top half of the unit circle. That angle's not on the top half of the unit circle. So no freshman dream there of just erasing and getting 7 pi over 6. All right, so, but we can evaluate very easily, and there's a ton of symmetry that's going to happen here. Cosine of 7 pi over 6 is negative root 3 over 2. So negative root 3 over 2, I'm going to draw a 12-sector circle up here because it's the geometry is, the symmetry at least, is definitely helpful to see. So 7 pi over 6 was right here. Now we're saying, what's the angle on the top half of the circle with a cosine value of negative root 3? And you can see that we just reflected right through the axis there. And the angle that we are going to end up with is 5 pi over 6. All right, let's do this nasty looking thing. Okay, definitely I want a picture. When in doubt, draw a picture. At least gives you something to do. Inverse sine is an angle on the right side of the circle. Okay. We have two choices. We could be in quadrant 1 or quadrant 4. It doesn't matter. Both will work. I'm going to draw a representative angle, and again, it doesn't matter. I just need to draw, I need to get something on my paper. There's an angle, and I want that angle to represent this right here. I'm going to call it alpha. Call it alpha. That looks like that. I want that angle right there to be alpha. Alpha. Okay, so it's negative something. All right. So that is an angle on the right side of the circle. I didn't say unit circle. Right side of the circle with a sine value of p-qs. P over q. Sine value of p over q. So what we have to do is draw a picture that will represent an angle with a sine value of p over q. You could choose a unit circle, of course, but it's a little easier in this case. If we want the sine value to be p over q, instead of choosing a unit circle, we could choose a circle of radius q. And then the sine value, right? Sine value is the y value over the r value. So that would be p over q. Everyone agree with that? If you chose a unit circle, you would have a 1 there, and then your y value would be p over q. Now we need to find that x value. We know that x squared plus p squared is going to be q squared. Pythagorean theorem. Solve for x. We're going to subtract off the p squared, and then we have to take the square root. And it's plus or minus. But what's true about every single x in that yellow area over there? They're what? Positive, yeah, not negative, right? It could be, it's non-negative. It could be 0 or positive. So we know, regardless of whether we drew this terminal ray in 4 or 1, still we have to choose the positive square root. Doesn't matter where we drew that terminal ray. Now we're good to go. We have the x value now, right there. So that x value, we just found it. Cotangent of this angle, by definition, cotangent is x over y. So now we can answer it. So it's x over y. So cotangent of, what was it, inverse sine of p over q. It's x over y. So it's square root of q squared minus p squared, all divided by p. That is how we would do it symbolically if we don't have angles that we can work with. Ooh, that's elegant. So definition of cotangent. Cotangent of any angle is the x value divided by the y value. We didn't know the x value. We chose to label the two of the three values here based on this expression. Inverse sine of p over q is the angle with a sine value of p over q. Sine value of p over q. We calculate x through the Pythagorean theorem, and then we evaluate cotangent as x over y. So that gives it to us. All right, let's pause. Let's pause for 48 hours. Minus 2 1/4. 48 minus 2 1/4. See you on Thursday.